Hello and welcome to the latest of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Aaron Wolf, here today for Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be moderating today's webcast. I'm now very pleased to introduce today's speaker, Dr. Jeb Or. Jeb is a Principal Staff Flight Systems at McLaren Aerospace. He supports commercial space and DoD programs and also serves as the technical specialist for the NASA Marshall Space Flight Center's Control Systems Design and Analysis branch. Dr. Orr holds a BSc in Computer Engineering and an MSc and PhD in Control from the University of Alabama in Huntsville. His research interests include flight dynamics, control allocation, propellant slosh, adaptive systems, and numerical methods. Jeb's talk today is entitled Launch Vehicle Load Relief, a Historical Perspective and Some New Concepts. A review of historical flight control approaches to launch vehicle load relief is presented, with an emphasis on the capabilities and limitations of acceleration and angle of attack feedback schemes. The basic dynamics and control principles of a rigid rocket are used to illustrate trade-offs and design considerations. The control laws used for NASA vehicles such as Saturn I and IB, Space Shuttle, and Ares 1X are reviewed. It is shown that modern, low-cost, strapped-down GPS INS systems, combined with pre-flight measured winds data, can be used to provide quality estimates of the angle of attack for use in modern load relief schemes. Now, I would like to turn the webcast over to Jeb.
All right, Aaron, thank you very much for the introduction, and thank you to the NESC for hosting not just the series, but this talk in particular. As Aaron mentioned, the title of today's talk is Launch Vehicle Load Relief, a Historical Perspective and Some New Concepts. We're going to talk about the background of load relief, what it does in principle, how it's deployed on large rockets for the application to large launch vehicles, orbital boost systems, and talk about some recent research that we've done with the NASC and others, ways to potentially modernize and improve those approaches for better performance. I do want to acknowledge my colleagues who supported this effort, Dr. Russell and Abram Alanis, who both work with our group supporting NESC. They were instrumental in pulling together a lot of the simulation and analysis results that I'll show here at the end. Okay. So launch vehicle load relief, the concept of load relief is, the idea is to reduce primarily transient bending loads on the vehicle. And in order to reduce transient bending loads, as control designers, we use rigid body load indicators as a surrogate or a metric to simulate the effect of or model the response that we would get from a full moment-based, bending moment-based load metric. So in very high fidelity production simulations, we will assess bending loads. An example of that type of simulation is shown on the right here for Ares 1, and I'll get into the details of that animation here momentarily. But in essence, from a flight control design perspective, the objective of a load relief algorithm is usually to reduce the product of dynamic pressure and the total angle of attack. If you're familiar with missile aerodynamics versus aircraft aerodynamics, alpha total is just the RSS incidence angle, or the root sum square of alpha and beta. So it's the total angle of attack of the vehicle with respect to the incident wind. It's worth mentioning here that in this presentation, we're talking about essentially rigid body load relief schemes with the implied or the implication that a high fidelity analysis is used, as we often do in production, to assess how effective reducing Q alpha total is at actually reducing the bending moments. And so there's a couple of caveats I want to point out at the front end, is that reducing Q alpha total doesn't always mean reduce bending moments. In fact, many large long flexible launch vehicles, Ares and Saturn being an example, what we found is that the moments due to gimbaling, in order to make Q alpha total take on a smaller value, and actually drive the loads up, sometimes in certain flight conditions higher than one would see with with no load relief or reduced gain load relief. So I do want to caveat that at the outset. But for the purposes of this introductory discussion, we're going to talk only about rigid body load relief approaches. We're not going to go into a lot of detail in terms of deriving various forms of load relief. We'll talk about conceptually how they work and show some examples architecturally from different launch vehicle programs. So most approaches to load relief use some sort of acceleration feedback. We'll talk about why, but essentially what we're trying to do with load relief is control angle of attack. It's very difficult to measure angle of attack directly, so we use a surrogate measurement like NZ and combine that with filtered angular rate in order to construct a synthetic, either an actual direct estimate of angle of attack or a surrogate signal that we can use in the control law. So I'll talk very briefly of this example over on the right here. So this is a transient, a high fidelity linear transient simulation of the Ares 1 vehicle with aeroelasticity and bending dynamics and propellant slot and TVC dynamics and so on. And what we're seeing here is the flight conditions, supersonic. The vehicle has a fairly aggressive load relief law, and the intent of the load relief law is to reduce the transient bending load. But you can see even with the aggressive turning into the wind, there's quite a bit of excitation due to aeroelasticity of the bending dynamics. You see that the sloshing dynamics get coupled in. The gimbal motion is, of course, induces bending as well. So the general takeaway from this is that, yes, for design purposes, we can look at the rigid body system, but this really is a very complex coupled problem. And that differs a lot, with the exception of very long, large flexible aircraft. For many aircraft and other aerospace vehicles, these dynamics can be separated and considered independently. In the launch vehicle problem, especially liquid propellant, flexible launch vehicles, large vehicles, these things have to be considered all simultaneously. So we'll briefly talk about the dynamics of the vehicle here at a high level. We'll talk about the rigid body vehicle. For this application, we're going to restrict the discussion not just to rigid vehicles, but rigid rockets on a gravity turn. Okay. Gravity turn assumption is a core assumption for most launch vehicle flight dynamics models where the vehicle is not spinning, angular rates are small, and gravity turn by definition is the alpha equals 0 trajectory. Now there are multiple potential gravity turns that solve a 2-point boundary value problem from the Earth's surface to some point in space, typically at like first stage burnout, where alpha equals 0 is satisfied, and those can be solved offline. They can be solved via various methods. But the key is the trajectory at every point along the trajectory, the equilibrium flight condition in the absence of wind is 0 load, 0 normal acceleration, and 0 alpha. All right, and because of that, the way that we formulate the design problem is not as in classical control theory terminology. It's not a servo problem, it's a regulator problem. So we are driving the states toward the gravity turn. And so we define, for example, the attitude error. We define, for example, phi y in this diagram here is actually the attitude error. So that's not like just an angle error, and then we have an additional command. Command is always 0. So it's really a regulator problem. So if the flight control system is able to regulate the error to the commanded attitude profile, which is this a priori gravity turn, then we achieve, in the absence of wind and ideal knowledge of the vehicle characteristics, we will achieve alpha equals 0 for the entire trajectory. And we can derive a couple of relations from these basic dynamics. The way that this frame is defined, this is the classic launch vehicle perturbation dynamics frame, kind of standardized in the very early the launch vehicle dynamics approaches that were developed by Halsherman and published by authors such as Frosch and Valley and the Saturn program and so on. We can define the angle of attack in a linear sense as a combination of the error, in this case phi y, which is the error with respect to the command gravity turn trajectory, plus the lateral velocity divided by v, and v is forward velocity. And that's just a small angle approximation for arctan, which gives the alpha component due to wind. So that second term there in alpha y is the translation component. There's no wind defined here. So there's an angle component and a translation velocity component. So, but you can reason from this is that if we accelerate the vehicle for some reason, normal to the trajectory, and there's a steady state velocity z dot, and this I here is a quasi-inertial frame. This is not a true inertial frame, but in a linear sense, it's an inertial frame. It's actually an accelerating frame that is accelerating with the vehicle and anchored to the center of mass. If we accelerate the vehicle ends up with a steady state velocity, even if we bring the attitude error back to zero because the vehicle is translating, there will be a constant angle of attack. And we have this really neat relationship. This is a little challenging to drive, but it falls out of the linearized dynamics, that the trajectory relative velocity, which is usually not easily measurable, the vehicle can sense its own velocity expressed in its own body coordinates, for example, via NIMU. But the trajectory velocity is not measurable, but the two are related if we have an estimate of the thrust acceleration. All right, so we have the mass times the body acceleration, the mass times the quasi-inertial acceleration, and then this effect due to translation. If you hold up a pen or pencil and kind of visualize this, you can imagine how it works. Imagine just balancing a pencil on your fingertip, and that's the that's your accelerating trajectory frame. So as you accelerate that, laterally back and forth, you have gravity, which is your F minus d times phi that provides a lateral acceleration. So we write all these dynamics in this quasi-inertial or trajectory relative frame. The reason is so that we get a linear expression for the angle of attack, and it's moving with the nominal center of mass location. Okay, and again, I want to emphasize all of this is with no wind. Okay, so the way I can get an alpha with no wind is I can either pitch the vehicle or I can accelerate the vehicle laterally, and the sum of the two of those things gives me approximately the total angle of attack. All right, so let's continue down the path of vehicle dynamics. Now, there are various ways to derive these dynamics. These are presented here in a kind of a standard form. Much as you see in aircraft dynamics, these two equations, where the translation and rotation dynamics are coupled. And the salient terms here that we look at, of course, we have the inertia tensor of the vehicle, the angular acceleration. We have, we usually, for large rocket aerodynamics, we break the force and moment coefficients into a single normal force coefficient and a center of pressure location. So this term, Cn alpha q bar S XCP, the XCP is the center of pressure location. That's multiplied by alpha to provide a pitching moment. And then we have on the right-hand side a moment due to gimbling, and that's, again, a linearized expression, beta command here. So this beta is not side slip angle, it's the angle of the VC system with respect to center line. And with all the rotations being right-handed in this case, this ends up being a moment. That's just xg, which is the distance to the gimbal. FR is the vectored thrust, and beta command, we assume that the achieved gimbal angle is equal to the commanded angle for simplicity here. So what we're saying there is the actuator dynamics can be neglected. And then we have something very similar for the translation equation, that we have lateral acceleration. We have this term that shows up due to being in this accelerating reference frame, which has G bar, that's that force minus drag over mass term. We have the normal force coefficient. Notice there's no XCP, so that's normal force. And then again, this expression for alpha. Okay. So what we'll end up here is typically, if the vehicle is stable, we'll end up with two complex poles for the rotational dynamics, one complex pole pair, and we'll end up with one real pole for the translation dynamics. And of course, we, in order to compute terms like phi, we integrate these with linear equations. We have to add additional states to integrate the angular rate and so on. But the takeaway is that we can call these rotation dynamics short period in analogy to an aircraft system, but they're almost always unstable without feedback control. And the reason is that the center of pressure is almost always forward of the center of mass location for performance reasons. When we look at maximizing performance and minimizing drag, it's typically cheaper from a drag and performance standpoint, although more costly and complex, to add thrust vector control to actively stabilize the vehicle. So most large launch vehicles are unstable, statically unstable in pitch and yaw. But once we close the loop on that system using, say, like the feedback control, we end up with two complex poles and one real pole. Those translation dynamics, I'll talk about them in this presentation. I'll call them a drift mode, or plunging mode. This is basically usually not directly controlled because we're not usually controlling lateral velocity directly. We're we're controlling acceleration, or maybe we're not controlling lateral dynamics at all. And so the location of that pole in the linear system tells us a lot about how the system is going to respond to initial conditions and how it responds to attitude perturbations and wind gusts. Does the vehicle turn into wind and diverge? Does the translation diverge exponentially? Does it essentially reach steady state, or does it return to the equilibrium trajectory? So the idea with load relief is that usually we want to have the two rotation poles be stable and well damped with a nice kind of like 0.707 type response. And we want the drift root to be at worst neutrally stable, where you can perturb it and it just looks like an integrator, and maybe the vehicle scoots laterally off the trajectory a little bit, but it doesn't continue unless it's actively disturbed. All right, so how do we usually formulate a basic control law for a launch vehicle? Well, it's usually just PD feedback control. It's neat when you go through the simplified dynamics. You can come up with a closed form set of gain expressions. If we just use simple proportional derivative feedback, where the commanded gimbal angle is equal to some error term, this is the perturbation from the attitude command. This is a proportional gain and a derivative term times the angular rate. You can go through an exercise where you set the characteristic polynomial equal to a standard second order form, equate the gains to a set of to a controlled natural frequency and damping coefficient. That's this omega c, it's theta c. And turns out if you know these parameters reasonably well, you can guess the KP/KD gains and come up with a response that for the rigid body system gives you really nice performance. Now, of course, you don't get the aggressive disturbance rejection you get with PID, so there is actually another set of closed form expressions that's a little bit more complicated, where you can design a PID control law for a rigid rocket, and you can see some of the differences between the two here on the right. So as is typical for most simplified classical control problems, PD can give you a really nice step transient response or initial condition response in this case. PID, you get a little more overshoot. Of course, in the presence of an external disturbance, PID is able to bring that disturbance in the steady state to zero, whereas you end up with a constant type offset for PD control. Going through this exercise, there are some neat metrics that you can pull out. Can go do a very high fidelity linear frequency response analysis, but actually for some of the low frequency dynamics, this estimate of the aerodynamic gain margin, for example, is really accurate. It's just basically the ratio of the pitching moment per unit error due to proportional gain over the pitching moment due to aerodynamics, and that gives us the so-called aerodynamic gain margin. All right. So the takeaway here is that we are simplifying the problem, but we're not simplifying the problem to the point of not having any utility. All right, so these are production type analysis that we use to form initial guesses for actual vehicle flight control systems. And then once we add bending filters and accommodate slosh stabilization and so on, these initial guesses can be modified via tuning or numerical optimization in order to produce a final set of control laws. Okay, so how do we take this very simple approach and incorporate load relief? Well, the most intuitive initial approach is to just do alpha feedback. So let's assume that I have a perfect estimate of angle of attack. So in order to use Q alpha total, of course, Q, in this case, Q bar dynamic pressure, in this frozen time linearized analysis is a constant parameter. So reducing alpha Q alpha total, I just need to reduce alpha. So I can add pure alpha feedback. Now, pure alpha feedback is actually unstable, or can be unstable at a certain level of gain. The vehicle will turn into the wind in order to reduce alpha or bring alpha to zero, and it will deviate from the trajectory. Now, this isn't necessarily a bad thing. It depends on what the vehicle is doing at that time and for how long. The way that we write the dynamics as perturbations with respect to an equilibrium trajectory, if you introduce alpha feedback, the vehicle will deviate exponentially from that equilibrium trajectory, which from a linear standpoint is a polar right half plane, and it looks like an unstable vehicle. Now, whether that's really bad from a how the vehicle actually behaves standpoint it depends very much on the vehicle design. But ultimately what you have is with pure alpha feedback at a sufficiently high gain, something more than about 0.5, it's actually 0.41 is the critical gain the eigenvalue associated with that translational dynamics of the drift route is in the right half plane the vehicle diverges. So what we can do is just, essentially the next simplest approach is use a linear combination of attitude and angle of attack feedback. So what we do is we take some of the attitude gain away, so we have this 1 minus kappa gain, and we add it back as alpha gain, and then we can just adjust this gain kappa between 0 and 1. So if it's equal to 0, we've got pure PD control, and if it's equal to 1, we've got pure alpha feedback control. Now, because we're doing we're doing attitude feedback either way, this ensures, regardless, that the rotational dynamics are stabilized. So you get approximately the same aerodynamic gain margin for the vehicle, whether you use cap equal 1 or cap equal 0. What this is controlling is what happens to the translation dynamics. So with a lot of algebra, it's possible to go through, and there's a derivation of this in the textbook by Dr. Barrows and myself, and this actually mirrors a much earlier result that was derived in a different fashion using the final value theorem for load relief. There's a critical gain case C where the drift route is in the origin and the system is neutrally stable. And that's a closed form expression, and there are various ways to formulate that. But it's a function of the control gains, the proportional derivative gains, the aerodynamics, and so on. And at that critical gain, the response to gust is improved, but the vehicle doesn't deviate exponentially from the trajectory. Now, of course, the choice of that gain is critical because it depends on all the system parameters. So if you design the system to put that route exactly in the origin, it's never going to be perfectly there due to parameter uncertainty. But that's not really a bad thing because the system's time varying and so on. So that's something that's verified in subsequent analysis. Now, ultimately, this ends up being equivalent to so-called drift minimum control, which we'll talk about in just a minute, which is a classical load relief approach. But the biggest issue we have is that we can't actually measure the angle of attack reliably. And we'll get into that in just a few minutes. All right, so I will point out here in the top right of the slide, if we look at just the attitude dynamics, I kind of made this assertion, feeding back Kp phi versus Kp alpha are nearly identical, and you can see that in the attitude dynamics. And the only reason these two initial condition responses are different is because the vehicle picks up some additional lateral velocity. So we're changing the coupling into the lateral mode here, and it's causing the attitude response to be slightly different. But at a 10,000 foot view or 10 kilometer view, this is essentially the same attitude response, but you can see the response to gust. So this is just a representative Ares-like vehicle. It's a made-up vehicle. 100 foot per second gust, which is equivalent to about a 3-degree transient alpha, and PD, of course, the vehicle picks up some velocity. But you can see with the alpha feedback that you get essentially a 1/3 or 25 or 40% reduction in the transient alpha, which of course translates into reduced loads. But what do we do about measuring alpha? Okay. So there's a lot of work done in the late 1950s, early 1960s in load relief schemes. Particularly, I think really the place it was first looked at very seriously was by several control design researchers at NASA Marshall Space Flight Center, Holker, Walter Hauserman, and so on. With the application to Saturn I and Saturn IB. And angle of attack sensing was strongly considered via vanes, forward-located vanes, as had been used for various aircraft systems up to that point, a lot of flight testings. There were, flight-qualified vane systems that would work out to reasonably high Mach numbers. It turns out when you take and put a vane system on a very flexible vehicle, the elasticity becomes a significant challenge because you have this primary bending mode of the vehicle. It's corrupting the local flow direction. It's hard to get an accurate, rigid body estimate of the angle of attack. I also want to mention, I'll have a sidebar on this because I've done a lot of work on the X-15, historical analysis of the X-15. So we'll talk about the X-15 ball nose, which is just a really neat thing to understand the principles, how it's designed. The X-15 ball nose at this point actually had been demonstrated out to, I think, by 1964, 65, it had been flown up to about Mach 5.5. But the challenge for launch vehicles is typically in the transonic regime, and the X-15 ball nose, as really the first, what we would almost call a flush air data system, could be used in this application because it wasn't reliable in subsonic and transonic conditions. The vanes, in addition to flexibility, you've got surviving launch environment, and of course at this point in history, inertial air data wasn't really practical due to instrument errors, without throwing strategic grade instruments at the problem. This was also tried on the X-15. There was actually a series of experiments late in the X-15 program to compare ball nose alpha to inertial alpha, and what was found at the time, again, is that the onboard computing capability wasn't sufficient with either strap down or gimbal platform to reliably compute angle of attack. So the community went to accelerometer feedback. This technique was borrowed directly from aircraft flight control systems that had been used extensively prior to the early 1960s. And the idea is that instead of feeding back alpha, you just have this gain KZ, and you bring in this body frame, Z body D dot. Right? And there's a lot of literature on this. There's a couple of references here I encourage you to go take a look at. These are publicly available. There are essentially three closed form gain sets that can be derived using the final value theorem for simplified launch transfer functions for steady state, of course. There's attitude error minimum gain, and I'll go through these with a bit of a cartoon here in just a second. In this case, the vehicle attitude error is 0. This is essentially a special case, very similar to that drift minimum condition. There's the drift minimum condition where the vehicle acceleration normal to the trajectory is 0 in the steady state. And then there's load minimum, which is equivalent to no alpha, or equivalent to pure alpha feedback. The vehicle angle of attack goes to 0 in the steady state, and the vehicle turns into the wind. Now, in the classic literature, what you hear that referred to is path motion, unstable path motion, but it's the same as what I mentioned in the preceding slides. All right. So this chart has been reproduced from an excellent figure that was done by Li Yang and Draper back in 2009 for the Ares program, and I've modified and adapted a little bit, but this really shows clearly these different types of gain parameterizations for their alpha feedback or equivalent lateral acceleration feedback with PD control. Now, if you add bending filters and you add PID, the situation changes a little bit, but at a conceptual level, this is a pretty good approximation. So what we have here is essentially 5 different gain parameterizations. We have the vehicle is, the nominal flight path is vertical along this nominal equilibrium trajectory. And we have an external wind from the left side of the page. And the shaded region is the initial vehicle's transient response to the wind. Okay. Now, if we start kind of at the right with only PD control, because the vehicle is statically unstable, initial alpha induced due to a lateral wind velocity will cause the vehicle to pitch away from the trajectory. And then in the steady state, the vehicle will return to 0 attitude error, but it will eventually accelerate to the point that the vehicle's lateral velocity with respect to the trajectory matches the wind velocity, right? And that, of course, is a drift condition and also has relatively high initial loads. Minimum attitude error is a special case where the attitude error returns to 0. The initial transient with respect to wind is minimized, or 0, actually, with perfect parameters, identically 0. And again, the vehicle does drift with the wind. This is actually a very valuable load relief formulation, but it's hard to, it's a special case of the parameters. It's hard to nail it exactly, but this has been used in production systems. All right. Drift minimum control. All right. So as you increase the accelerometer gain or alpha feedback, the vehicle will turn initially into the wind. And in the drift minimum condition, the vehicle reaches a steady state where even in the presence of wind, the vehicle reaches a steady state where it is canted into the wind and is not accelerating with respect to the equilibrium trajectory. And the displacement, this is a classical control, quasi-steady state type 1 error type system. or sorry, type 0 error type system, the displacement from the equilibrium trajectory reaches a constant that's proportional to the magnitude of the disturbance. And then pure alpha feedback above a equivalent alpha of about 0.4, 0.41, the vehicle will turn into the wind in order to minimize alpha, but of course it drifts away from the trajectory in the opposite direction, and that drift is unstable. So this is a really helpful way to look at all these different conditions, and we won't go into the details of how these are derived, but some of those references that I provided can be, if you skip over those, there's detailed derivations of these conditions from the quasi-steady state final value theorem type approach. All right. So load relief in Saturn. So it was shown during Saturn I, Saturn IB, and then subsequently in Saturn V that pure accelerometer feedback is actually really difficult to stabilize. And the reason is it's not a perfect accelerometer located at the center of mass. The bending dynamics are strongly coupled into the accelerometer feedback signal. You can see here with this image of the first bending modes of the Saturn V. The IU, the control accelerometer, is located in the instrument unit, which is up here. You can see the mode shape amplitudes at that point are quite significant, and so this requires aggressive low-pass filtering when using classical control approaches to provide frequency separation between the accelerometer feedback and for the rigid body and the bending dynamics, and especially in the Saturn case, using analog filters. This really wasn't achievable, and as a result, initially angle of attack feedback was abandoned for Saturn I, Saturn IB in favor of the accelerometers. Then, even though it was baseline for Saturn V and shows up in the Frost and Valley paper as they discuss in the paper, it was eventually removed for various reasons. One of which was these secondary coupling effects couldn't be adequately stabilized using analog filters with component tolerances included, and the loads due to thrust vectoring actually got a little worse when the full stack-up was done. The other challenge we have is the same for using accelerometer feedback on aircraft or NZ. Since the accelerometer is not at the CG, there's a strong, sometimes non-minimum phase coupling into angular rate, which requires angular rate compensation or construction of a so-called synthetic IMU location. Some techniques are used for missile feedback and so on. When flexibility is considered, it's possible to actually decrease the effective closed loop bending damping as a result of using accelerometer feedback, which goes against the other control objective, sometimes in large launch vehicles, providing active stabilization in the first bending mode. All of these things have to be considered, and when you stack all of them up on something large like Saturn V, it's really hard to make it work, and that's why it was eventually. All right, so real quick sidebar on the X-15 cue ball, since I mentioned it. This is just a really neat thing. It's just an incredible piece of engineering, very simple concept. So a lot of us in the flight control community are familiar with the idea of a FADS or a flush air data system, where you have pressure sensors that are sometimes redundant on the forebody of the vehicle, and then you've got a CFD and wind tunnel correlated pressure distribution table with respect to alpha beta. You try and measure the pressures, you put them through an estimation algorithm online, and you extract an alpha beta. This has been demonstrated on shuttle entry, not in closed loop, but it's been demonstrated. It's been used on several vehicles. It's very complicated, relies on a lot of analysis, a lot of sensors. X-15 had an alternative idea. This was formulated in the late 1950s and flown in the early 60s all the way up through 1968, all the way up to, I think it was demonstrated up to Mach 6.7 or so, and with an accuracy of about a half a degree, about a tenth of a degree of that, which was misalignment accuracy. And the idea here is that we know the ideal theoretical pressure distribution of a sphere in supersonic or hypersonic flow. And so if we have two pressure ports on that sphere, instead of trying to look at the differential pressure and correlate that to alpha, we just move the sphere until the pressures are equal, and whatever the angle of the sphere is the angle of attack. And so the X-15 so-called cue ball or ball nose just did that in 2 degrees of freedom with 4 ports, and was able to achieve very fast dynamic response and excellent measurement accuracy. If you're at the Smithsonian, or there's 2 surviving airframes, take a look at the ball nose up close. It's a really neat thing to see. This is a really innovative concept, could potentially be used for hypersonic systems that like X-15 for entry systems, for example, but for launch vehicles, it's not reliable enough at transonic and subsonic Mach because the flow characteristics over the sphere are not very well behaved to flow separation. So let's talk briefly about Space Shuttle ascent load relief. So shuttle ascent load relief was an implementation very similar to Saturn I, Saturn IB, combining NY or lateral and NZ normal feedback with day of launch wind biasing, which I'll talk about in just a minute. A system that was kind of independent to do Elvon hinge moment load relief, and this used delta pressure feedback in the actuators to try and essentially allow the Elvons to trail and respond to loading changes and not overload the Elvon structures. The key difference between Saturn and Shuttle, because Shuttle was not a zero lift configuration, although it flew a zero lift trajectory, is that there was a reference acceleration. And so load relief in Shuttle was actually flying to a reference acceleration. Now, as some listeners may know, there were quite a few flight control anomalies driven by aerodynamics errors on STS-1. And one of the things that really worked well despite those errors was the ascent load relief algorithm. So if we go look at the flight data for STS-1 and you compare the pre-flight predictions of any of the major trajectory parameters versus flight, most of them are pretty significantly different except for the angle of attack, and that's because the load relief NC feedback worked really well. This approach used on Shuttle, in addition to the algorithm design, kicked off this very kind of complex but now almost standard analysis process, which was looking at this coupled loads and dynamics problem and looking at these what NASA coined squatchaloids, which were alpha, Q alpha, Q beta limits that were specific to the vehicle configuration as a function of flight conditions. So a huge amount of analysis that was done, and those were used to develop the loads analysis cases and also set the requirements or the design targets for the load relief algorithm. Of course, as is true with all load relief algorithms, Shuttle was challenged, even being a relatively stiff vehicle compared to some of these very large, long, slender launch vehicles. It was challenged by issues with bending stability margins, and there were changes to how the bending modes were modeled late in the program, which then violated requirements against which the load relief law was assessed. And so these are recurring themes that we see in all launch vehicle flight control design problems. All right. So we'll look at the block diagram here for the shuttle ascent pitch axis FCS. This is from the JGCD publication reference below. This is a great paper, by the way, because it's publicly available and discusses all the flight data from STS-1. But you can see the very basic components. We've got sense normal acceleration, some gain and filtering here. And then we've got rate compensation, which essentially is just a high pass filter, takes the angular rate and approximates the angular acceleration to subtract that effect. And then that gets fed back into the inner loop control law. So not really much more complicated than what was done on STS, although on Saturn, just the analysis process and the design process was much more involved. So we'll look very, very quickly here at Ares 1, Ares 1X, and SLS. A little bit more complicated approach. This was a design using a little bit different paradigm, but ultimately analytically can be reduced to the same type of feedback formulation. Designed by Bart Bacon and his team at Langley going into the Ares 1X program. And the idea is that you kind of build this force and moment diagram of the vehicle and you try and simultaneously achieve force and moment balance. It was modified for Ares 1 and subsequently SLS to decouple the force balance part, which provides a load relief function, a moment balance part, which provides a disturbance rejection function. And by decoupling those, you get a lot more design latitude. But this is, from the Ares program, very typical results for large flexible launch vehicles. For Ares 1, the first, bending mode was phase stable. So we were concerned with decreasing bending mode damping with the inclusion of load relief. And statistically speaking, this is pretty typical. on a full production system with bending dynamics and slush, load relief bandwidth is about 10 seconds, tenth of a hertz, and the mean Q alpha total decrease is about 7%. So this is not a solve all the loads problems type of approach. It's a do a little bit better, increase the margins type of approach. All right. Okay, so that's kind of where we've come to, and our team very recently, with some support from NESC, looked at are there ways that we can use modern data sources, such as improved INS, GPS INS, and combine them with novel steering approaches to re-architect how we do load relief and maybe get some performance. So the idea here is, can I take the load relief scheme out of the inter-loop FCS and actually put it outside and do like more of a classical control multi-loop closure type approach? And the goal here is to step away from this idea that everything needs to be in the inner loop and be very high bandwidth. And inner loop feedback necessarily increases the dimensionality and complexity of the control design. So if we look at SLS, the SLS autopilot, our team was involved in the design of that system, particularly the inner loop autopilot and the active control and the load relief. We look at the autopilot. We've got 3 primary control gains. There's a ton of filters, basically 64 filter coefficients, and 4 load relief gains for each of the pitch and yaw axes per flight conditions. So it's a huge optimization problem. Now you get a lot of design flexibility, but for maybe smaller, more agile vehicles, can we simplify that a little bit? Now we still can't really do direct air data sensing and do pure alpha feedback. It's not feasible and reliable. Things like FADs or 5-hole probes, issues with weather and launch availability. We had an issue on Ares 1X where the 5-hole probe was contaminated with water prior to flight, which affected the availability of the data for post-reconstruction. But GPS INS capability is really improved in the last 10, 15, 20 years. So what we found is that if you have reasonable accuracy GPS INS on the vehicle, and combine that with good day of launch measurements, either from balloons or radar, that it's possible to construct a synthetic angle of attack estimate that's of very, very good quality. So we have access to inertial air data, and in the interest of time, I'll speed up just a little bit here. But if we look at this is actually a nice high fidelity simulation, and for various reasons I can't include the details on the INS, but this is a medium tactical grade IMU with GPS dating, running in a high fidelity covariance analysis, and just based on inertial data alone, without winds, we're able to estimate alpha with a 1 sigma covariance of about 1/10 of a degree. This is excellent. And the key there is that by using GPS information to estimate the error statistics in a traditional 21 state EKF navigation Kalman filter, we can take out a lot of the error terms that or reduce a lot of error terms that would corrupt the angle of attack estimates. And then if that's combined with Doppler radar wind profiling or balloon soundings, which are all standard range products, or even forward-looking sensors, LiDAR, et cetera, we can formulate new control laws to take advantage of that angle of attack data. Okay. So example of day launch iLoad, iLoad update. The biggest challenge with this today is that there's not a lot of good statistical data for the major ranges like the Wismar, Vandenberg, and the Eastern Range on the statistical correlation of the measurement versus actual, because there's an independent measurement of actual. Now there's some data on that differences where we've looked, where NASA has looked at Doppler wind profiler data versus balloon data at the Eastern Range, but that's a challenge. So we use reasonable conservative estimates to build up these error models. For example, filtered random walk and a Gauss-Markov noise model that captures the spatial and temporal error in the winds measurements. But even with pretty gross errors, we're still able to provide pretty reasonable estimates of angle of attack. A little short on time, so I'll go very quickly through this, and of course the slides are available for review. I want to make sure we leave enough time for questions, but essentially what we have done is we've taken those gravity turn equations, we've added a term due to wind. This is just a standard term due to wind, so you end up with, now instead of just the lateral velocity over v, you've got the wind velocity over v. And it turns out if you can measure the alpha, you can take an extra time derivative, come up with an alpha dot term, and this falls out of a technique that's used for tail-controlled missiles for actually doing normal acceleration control. We just back up a step and use it with the gravity turn assumptions to come up with a control law that does alpha control or alpha regulation. And what we end up doing is coming up with actually a guidance law that we can wrap around the inner loop that uses rate command feedback and knowledge of acceleration and the alpha to provide a PI-like response that's very well damped and relatively high performance and really just doesn't perturb the inner loop at all. What we find is that we can tune the inner loop separately, so the inner loop stability margins aren't affected by the outer loop closure. The inner loop autopilot stays very simple. It's just a PD or PID control law with bending filters, and then we can reduce the effective acceleration feedback gain. So all these things point towards more tunability, better performance, and better stability. Now, this is not a, this modified approach is not a solution to all problems. We still have to deal with bending and the accelerometer feedback. There are some cases at low velocity where the acceleration feedback gain is high. And we don't get away from the fundamentals of the dynamics, is that the drift route is still going to be unstable for the load minimum condition. But what have we done in deriving this approach? We've come up with a control law that simultaneously considers all the linearized dynamics and kinematics of the vehicle in formulation, rather than just inserting one term and then trying to tune around that term. All right, so we went off and simulated this in a high fidelity production launch vehicle simulation. We maintain internally this single stage liquid propelled vehicle model called SysTV. This is a synthetic vehicle. It's essentially a CDR quality model, but it's not tied to an active program, so there's no program sensitivity, which is we can show the results across the agency and externally. And we looked at comparing no load relief, with GPS errors but perfect dolly loop, meaning we know the wind exactly, and then load relief with GPS and dolly loop errors included. And we went and did a full production Monte Carlo analysis on the system, 2,000 runs each. I'll show the results real quick here. So of course we don't fly it through the entire trajectory. We're looking at delta, so we turn the load relief law on at T40, which is just going into maximum dynamic pressure. And what we see is a very rapid and graceful reduction in Q alpha total that exceeds significantly the performance that you can get with just pure alpha inner loop, pure alpha feedback, or NZ feedback. And of course, when we include dolly loop errors, we have, for example, the nominal trajectory is a little bit worse because we're actually picking up some error due to the winds estimates in the nominal case as well. But overall, this is a very exciting result and shows that by kind of rethinking load relief in the context of, what can I use if I use all the information simultaneously that I have available to me, take advantage of high performance GPS INS systems, and also formulate the control law, being cognizant of the whole system dynamics without doing a lot of nonlinear dynamic conversion or anything. It's all linear dynamics. But if I do all those things simultaneously, I can actually improve the performance, 20, 30, 40% over this baseline type of alpha feedback or NC feedback. Okay. All right. So load relief, in summary, is a very powerful augmented control technique to reduce transient loads due to wind in large launch vehicles. And this is something that's been around since the late 1950s, early 1960s. So these techniques, have been essentially unchanged since the early 1960s, and that's because they generally work. Now there are some areas where we can potentially improve, and that's what we've been looking at lately. Ultimately, what's the goal? Reductions in loads improve margins, they improve safety, and ultimately they can reduce structural mass, which can improve launch vehicle performance. All right, so things to keep in mind in the design process: placement of the accelerometer with respect to the CG. How it factors in with the bending modes of the vehicle, whether direct alpha sensing or alpha estimation is feasible, if the range at which the vehicle is flying has those assets like radar or balloons, the timelines for ConOps associated with the availability of those range products, how difficult it is to tune the control loop, considering things other than rigid body load metrics, like transient bending moments due to TVC, which I've hit on a couple of times, stability margins, and then this idea of, from a flight certification standpoint, of accepting temporarily or unstable or marginally stable path drift due to wind. But in summary, in most cases, these traditional alpha feedback or NZ feedback approaches provide a lot of benefit, but there is some room for improvement using modern strap-down GPS INS systems. And what we've demonstrated is relatively simple, but it's still just a linear control law that can be designed and tuned using classical loop shaping techniques, frequency response, stability margins, and so on. Okay. So I'll wrap up there, and we have just a few minutes for questions, and we'll still be on schedule.
Thank you for sharing with us today some of your knowledge and insights on launch vehicle load relief. That was an interesting presentation, and there are a couple of questions from the audience, but not too many. Anybody who has questions is encouraged to submit them via the chat, or actually we can just open the floor right now to anybody who has a question for Jeb.
So I do have one question. So I'm not quite clear on what the current SLS baseline is versus these other improvements that you think could be done.
The current SLS baseline, I'd be happy to share some publicly available papers on the SLS flight control architecture. The baseline is essentially traditional NZ feedback with a moment balance type, what we call DCA, or disturbance compensation algorithm. So it's very similar to what was flight demonstrated on Ares 1X, although we've kind of split the algorithm into two parts where we can tune the individual parts individually, or separate the parts and tune them individually, so as to get better performance and flexibility in the design. So what we've shown here is not, in terms of an advanced approach, is not part of the SLS baseline.
Thanks.
Although I will mention there is, I can't speak to it in this forum, but there is an opportunity that we may be flight testing this approach in the next 24 months.
Flight testing where?
On a launch vehicle system.
But not SLS.
Not a NASA launch vehicle system.
Yeah, okay, thanks.
Is this a dedicated flight test?
It is not a dedicated flight test for this flight control law, but it is an experimental launch vehicle platform, and you may have an opportunity to test this approach on that platform.
Thank you. Interesting. There was another request for a copy of the enduring legacy of Saturn V launch vehicle flight dynamics and control design principles and practices, which I think was a paper that you mentioned during the talk. Can we make that available along with the references that you were just talking about, Deb?
Yes, so that is that was a paper published in the International Astronautical Congress, and I don't think I can post the paper publicly, but if you email me, I will provide you a copy directly.
Another, another area that of questioning that might be interesting to talk about for a minute is, your analysis is based on linearized gravity turn assumptions and other kinds of linearized assumptions. When are those assumptions not valid? When do they start to break down?
Yeah, that's a very good question. So essentially everything that we've shown here is applied to a specific class of large launch vehicles that are typically relatively slowly ascending multi-stage systems that are intended to put payloads in orbit. there's a lot of literature on how those linear equations are built, but the fundamental assumptions are the angular rates are very small, in the order of a degree or 2 per second, that the angles of attack are close to zero, that the thrust vector control angles are close to zero. So these types of dynamics don't apply if you have a system spinning, if it's spin stabilized, if it's maneuvering rapidly, if it's pulling a constant angle of attack or constant lateral acceleration. But for most orbital ascent systems that are not going through aggressive maneuvers, these linear equations work really well.
Thanks, Jeff. Are there any other questions from the audience? If not, I guess we can sort of wrap it up, which would be unusual in that we're actually wrapping this up pretty much on time. Thanks, Jeb, for responding to the questions. If you have any additional questions, please feel free to pass them on to Jeb, or you can email me or Neil Dennehy directly, and we'll pass them on to Jeb so he can respond to them directly via email. The next GNC webcast in our series is titled Digital Engineering, Enabling the Complexity of Future High-Integrity Space Systems, with speaker Ossi Saarela of MathWorks. Ossi's talk is tentatively scheduled for January 19th, 2022. The webcast planning committee, consisting pretty much of me and Neil and other interested GN and CTD team members, is always looking for ideas for future webcasts that will be of interest to the GN&C community of practice. So if you have ideas for other relevant GN&C webcast topics, please contact Neil Dennehy. Thank you for participating with us today, and I hope you can join us again at our next GN&C webcast event. This completes today's NESC GN&C webcast, so bye for now.